You've probably seen that famous video from space, the one with the spinning T-handle that has baffled people for decades. But what if the official explanation for it is completely wrong? Today, we're digging into a very different take on one of physics' most hypnotic mysteries, the Dzhanibekov effect. All right, so this is the heart of the mystery, right? You see an astronaut spin this T-shaped handle in 0G. It's moving along, spinning, and then, bam, it just perfectly flips itself over and then flips back again, all on its own. It's beautiful, it's weird, and it's called the Dzhanibekov effect. So what is actually going on here? So the story really kicks off way back in 1985. A Soviet cosmonaut, Vladimir Dzhanibekov, is up in space and he notices this little wing nut that he'd unscrewed it's doing this bizarre, predictable flip as it floats and spins. It turned out to be a perfect real-world example of a physics problem that is deeply counterintuitive. Now, if you look this up, the established scientific explanation you're going to find is called the intermediate axis theorem. You might also hear it called the tennis racket theorem. It's a mathematical solution, and it's been popularized by some big names like mathematician Terry Tao and in awesome videos from channels like Veritasium. It's the official story you'll find in the textbooks. So what is this theorem actually saying? Well, basically, any object has three main ways it can spin. Think of it like a book. You can spin it end over end, you can spin it like a frisbee. Those are stable. But the theorem says if you try to spin it around that middle or intermediate axis, well, that's inherently unstable. The math predicts it's going to wobble and then inevitably flip all by itself. And this is the absolute key to the whole mainstream idea. For this mathematical explanation to work, you have to assume there are no outside forces, no external torques, no pushes or pulls, making that flip happen. The instability is supposed to be purely an internal property of the spinning object. Just remember that, no external forces. It's going to be really important in a minute. Okay, so that's the textbook answer. But what we're diving into today is based on a paper by an independent researcher, Mathis, who says, hold on a minute, and challenges this entire explanation. He argues that the standard model is missing something really, really fundamental. And Mathis really zeroes in on this one point. His whole critique is built on this idea. He says that the no external torques thing isn't a proven fact. It's just a huge assumption. He basically argues that physicists couldn't see or measure a force, so they just decided one didn't exist and then built this really complex math to explain it away. So this raises a really simple but powerful question. If the flip is all internal, what starts it? What's the trigger? The math can describe this instability, sure, but according to this critique, it never actually explains the physical cause for that first tiny nudge, that little bump that kicks the whole process off. Okay, so let's unpack this critique a bit more. Mathis points to two big problems. First, as we said, this bump just kind of appears out of nowhere in the explanation. Second, he claims the math does something he calls a cheat. It switches its point of view. It goes from watching the object fly past you to pretending you're riding on the spinning object. He says this is just a mathematical trick to invent internal forces, like centrifugal force, instead of finding a real external cause. And it gets even more fundamental. The critique claims the standard model messes up some really basic physics. It says the theory uses this mysterious bump, which is a single one-time force, to explain why the object accelerates into a flip. But basic physics says a single push just changes your speed. To get a real acceleration, you need a constant force pushing on it. Then the author brings up what he sees as the smoking gun, an experiment done on the International Space Station. It showed a cylinder that was spinning on its stable axis, not the unstable middle one, and it also started to wobble. According to this critique, the intermediate axis theorem has absolutely no way to explain that. Okay, so if the mainstream idea has all these holes, according to the source, then what's the alternative? Well, the paper offers up a whole new mechanism, something it calls the charge field. And this is where things get really interesting. The author proposes something called an ambient charge field. The idea is that there's this constant universal field of photons rising up from the Earth that mainstream physics has just completely missed. He's saying that space isn't an empty vacuum. It's an environment filled with this energetic field that's interacting with everything inside it. So how exactly would this charge field make the T-handle flip? The author lays out a step-by-step physical process. First, the object is spinning inside this field of rising photons. Second, because the T-handle isn't a perfect sphere, it creates these uneven swirls, or vortices, in the field around it. Third, these vortices then apply a real, external, and, importantly, constant force on the object. And fourth, that constant force is what causes the acceleration that makes it wobble and flip. So, from the author's perspective, this charge field idea neatly ties up all the loose ends. It gives you the initial bump from a real external source. It provides that constant force you need for acceleration. It could even explain why an object might wobble on any of its axes, like that cylinder on the ISS. And for him, this is the most important part. It gives you a physical, mechanical cause, not just an abstract mathematical description. But the paper doesn't just stick to the physics. It takes things a step further and gets into the why. Why this alternative view isn't part of the mainstream conversation. Now, according to the source, there's a reason this footage was supposedly kept quiet for so many years. The author claims it wasn't because of fears that the Earth's magnetic poles might flip or anything like that. Instead, he claims the Soviets were afraid that mainstream physicists would look at it and realize it was solid proof of a powerful ambient field. Something just like the one he's proposing. So really the biggest takeaway the author wants you to have is this. Always be a little skeptical of any explanation in physics, no matter how elegant or complicated the math is, if it doesn't have a clear physical, mechanical reason for why something starts moving in the first place. His point is that math is supposed to describe reality, not create it out of thin air. And that's really where the source material leaves us. It presents this detailed critique. It offers up a completely different physical model, and ultimately it just asks, is the accepted explanation the full picture? It's a fascinating look at how one simple, strange little flip in space can open up a whole universe of questions.